In the last video, we talked about acute injuries, and something that we might have implicitly implied when we talked about an acute injury happening when you go up the stress-strain curve and you get into this plastic region is that this idea that maybe if you went up the stress-strain curve but you didn't go out of the linear region, like if you just went up to here and you came back down, that wouldn't cause any damage in a tissue. And it turns out that is not actually the case. It turns out that if you go up and down and up and down and up and down the stress-strain curve many, many times, you will actually get damage starting to accumulate inside tissue. And that is what we call an overuse injury, which is what I want to talk about in this video. So we might think about overuse injuries as being like the gradual, slow accumulation of damage in, say, a tendon or a ligament or cartilage or bone. So instead of getting major, like a complete tear through the collagen fibers of a tendon, for example, if you go out and you do some maybe plyometrics training, you're going to do a little bit of damage to your collagen fibers. And then if you keep doing training and at a rate faster than your body can adapt to, you will have this microscopic damage that eventually starts to accumulate. And if enough of it accumulates, then you can get an overuse injury. And in fact, if you keep training on it, that can turn into a complete macroscopic damage, like a tendon rupture. So before jumping into graphs and numbers, I want to sketch out how you might maybe experimentally test or study this phenomenon. So maybe you would make a machine with two little clamps on it. And what you could do is get, say, a bunch of tendons from a cadaver and clamp them between two little like grippy things. And then what you could do is you could just pull on it and release it many, many, many times. So just stretch the tendon and release the tendon, stretch it, release it, and do that many, many, many times. And you could maybe record the force and also the cross-sectional area of the tendon. So in other words, you would know each time you pulled it, you would know how much stress, mechanical stress, you were inducing. And indeed, if you did this, you would find that after some amount of time, your cadaver tendon would eventually break. And I think you're all familiar with this phenomenon of it's called mechanical fatigue. And there's two very common examples of it. One of them is a paperclip. So if you take a paperclip and you bend it back and forth, eventually it will break, right? And another common example is a hair scrunchie. So if you have hair scrunchies and you use them for a long time, you stretch them out and relax them, and eventually they will break. And what's interesting about hair scrunchies is that they tend to break at the part where the two ends are fused together. So if you could zoom in on that, it would look like this. The elastic comes together and it's kind of like glued to the other end in this narrower part. And it's interesting that hair scrunchies tend to break right here. And we could think about that from a stress perspective. So you're pulling on, you're stretching out, you're putting tensile loading into the hair scrunchie at some amount, and that force is getting divided by cross-sectional area to create mechanical stress. So out here, that force is getting divided by this cross-sectional area. But in here, the same force is getting divided by a smaller number, so the stress is bigger. And that actually explains why hair scrunchies tend to fail right here. And the same is true for biological tissues. So continuing with this idea that you're doing this experiment, maybe instead of stretching one cadaver tendon until it breaks, maybe you get like 100 of them. And you decide to try out a bunch of different maximum amounts of stress because, again, drawing a stress-strain curve here, you know that if you pulled on this cadaver tendon enough, you would start damaging it and then it would break. So maybe when you're doing your experiment, you go up the curve to like this amount of stress right here. And you just do that over and over and over again, and then eventually it breaks, and you record how many times it takes to do that. Maybe you do another experiment and you decide, well, okay, this time I'm not going to stretch it as much. I'm only going to stretch it up to this level of stress. So in other words, I'm going to pull on it not so hard. And maybe you do this many, many times over and over and over with many different identical or identical-ish cadaver tendons. You could make a plot of it, of your experimental results. And here's how you would do it. What you would do is you would plot on the y-axis maximum stress, which we could think about that being how hard you pulled on it. And when I say stress here, again, I mean that mechanical definition of force divided by area. So maybe at some high level of stress, you pull on your cadaver tendons and they break after only like 3 or 5 or 10 repetitions. Well, we could plot that on the x-axis. Let's plot for each level of stress. So maybe we try this one a little bit lower, a little bit lower, a little bit lower, a little bit lower. We could plot the number of loading cycles it takes to break the tendon. So let's say number of loading cycles to failure. And of course there'll be some dispersion, some kind of some random chance, but maybe you try 10 tendons at each of these maximal stress levels. What you'd see is something like this. And maybe you take the average of each of them. So we'll average those experimental results out. Now, I'm going to fill in the x-axis here. I'm going to do something called using a log scale. So I'm going to plot it as not as like 10, 20, 30, 40, 50. I'm going to plot it as, because this is what it looks like when in these graphs, 10, 100, 1,000, 10,000. So we're multiplying by 10 each time we jump up. So a curve like this has a name, and it's a very common thing to do in engineering if you want to know how strong a material is. This is called an SN curve. Stands for stress and number of cycles to failure. So this curve has some important implications for how we would think about overuse injuries occurring and what the implications of that might be for programming, meaning exercise programming. So we'll go into that in a future video, but something to notice is that if you increase the stress, like how hard you pull on something, by a small amount, meaning you go over this way a little bit, you dramatically decrease the number of loading cycles it will take to create failure. So we'll go in detail on this in the next video.